So, we have seen that how this acoustic wave will be represented in the mathematically in the form of rotation and strain matrices, and it was the discussion was only about the acoustic wave, how which of the elements will be presented will be present there in the elements, and also that the nature of the acoustic waves in terms of whether it is a longitudinal acoustic wave or it is a transverse acoustic wave. If it is a transverse acoustic wave, which is actually which has two polarizations, that is, if it is travelling along x, it can have a y polarization or it can have z polarization, but these two are, we have seen, they are degenerate polarizations, and in the case of mixed polarization, that part also we have analyzed. And now we will bring in, we will connect this this nature of the acoustic wave in the medium, that is in terms of the amplitude, and that we will connect with the impermeability tensor, and how this optical properties will be changing in the medium, that part we will now discuss. So, we will look at this photoelastic effect and this elastic deformation, how this relative permeability is modified under the propagation of acoustic wave due to the periodic strain present in the medium, and then we will talk about, we will see the form of the photoelastic and that is strain optic tensor. Then we will look at the index ellipsoid without strain, without the presence of the acoustic wave, that is the natural refractive index of the medium, and then we will see how the strain is modified, how this index ellipsoid is modified under the strain. We will see that symmetric nature of the impermeability tensor and then the strain tensor put together. We will apply this index contraction rule to make it only a 6 element column vector. Then we will represent the index ellipsoid. We will take the example of strain optic tensors and the relation of the permittivity changes. So, that will complete the understanding of this acoustic wave with the impermeability tensor of the medium. So, we will try to bring in how this acoustic wave is changing the refractive index properties periodically along the length of the direction of propagation of the acoustic wave. So, elastic deformation, that is the mechanical strain in the medium that changes the optical properties. This is because it creates a periodic compression, periodic deformation in the medium along the length of the propagation of the acoustic wave. So, and this change in the refractive index or the optical properties, that stays back as long as the deformation exists. That is, so long as the wave is propagating in the medium, this deformation will be there. The moment it is not there, it comes back to that an elastic nature, it comes back to the original natural state, which will be represented by the normal index ellipsoid. So, elastic strain induced change in the relative permittivity, that is how we look at this photoelastic effect. So, under deformation or this mechanical change, this modified relative permittivity tensor is given by this, where this is impermeability in presence of the strain, this is impermeability without strain, and this is the change induced, this is the strain induced change in the impermeability, which can be represented by this tensor, that is P I j k L S k L. So, this is different from the one which we have discussed in the case of electro-optic effect. This tensor is called the strain optic tensor. So, eta I j the relative permeability tensor, and S k L, that is the strain tensor, which we have discussed. We have two components, strain and another is rotation. For the rotation, this p I j k l will appear in a different way. We will not consider in this case. We assume all pure longitudinal wave and pure shear wave. S p I j k l, that is the strain optic coefficients. So, we will see in details what are the forms of these tensors. So, let us recall that the index ellipsoid in the compact form is x I j by n I j scale. This is refractive index. In terms of impermeability, one can write in this form, and therefore, we can write this index ellipsoid in the compact x I eta I j x j. So, this is column vector, this will be this is a row vector, this will be a column vector, and this eta I j will be I cross j matrix elements. In this case, it is 3 by 3. So, 9 component element. We have seen this earlier also. So, the exact form of this is x y z. You have eta 1 1, eta 2 2, these are the diagonal elements, these are the components of the impermeability tensor. So, the modified, if it has to represent this modified index ellipsoid, then this eta 1 1, all the elements. So, this matrix is also the modified matrix, that is, this is the sum of this matrix with no acoustic wave plus the change in this matrix in presence of the acoustic wave, which is represented by this equation. So, this is the sum of the impermeability without the strain and the change in the impermeability in presence of the strain. So, this is the sum of these two is represented by this in the case of modified index ellipsoid. Okay, now, in the principal axis system, we have eta 1, eta 2, eta 3, these are the principal impermeability components. Equation of the index ellipsoid is this, which is in the principal axis system of the medium, and that is all when there is no strain, there is no deformation, there is no acoustic wave or anything, is under the normal state. In terms of impermeability, this equation can be written in this form, because 1 by n 1 square is eta 1, 1 by n 2 square is eta 2, and so on. In a non-magnetic dielectric medium, this is a symmetric tensor, and eta I j, eta j I, because of the symmetric nature, which actually helps in the index contraction. We will see how this symmetric nature reduces the task of this algebraic manipulation. 1 by eta square I j equal to 1 by n square j I. Okay, so, in the explicit form, that is, if I have to consider all the elements, that in, then it is x 1 square, x 2 square, x 3 square. So, again this is the complete form of the general form of the ellipsoid equation, this equation, and when it is modified. So, this is again a symmetric nature of the tensor. So, these two of the things, that is eta 2 3 and eta 3 2, they will be put together with a 2, and similarly x 1 3 x 3 1 will be put together because they are symmetric. So, that is again 2, and so on. So, you actually compress this 9 elements to 6 elements because of the symmetric nature of this, and that helps. So, the index contraction rule is x x is 1, y y 2, these are the diagonal elements, y z, z x and x y, they are the off diagonal elements. So, this x 2, x 3, x 3, x 2, that is will be represented by this 4. So, using this, we can write this equation in this form, index ellipsoid form. In the compact form, with the contracted index eta 1 x 1, eta 2 x 3, and so on, is equal to 0. So, this reduced equation now it takes this form, because now we are using this x 1, x 2, x 3 in place of x y z, and it becomes eta 1, eta 2, eta 3, which is again very straightforward and very simple algebra to understand. Now, the modified tensor, which we have mentioned that this is in presence of the strain, this is in absence of the normal state, and this is the change in the impermeability because of the strain. So, this has the form of this. So, because delta eta, because of the symmetric nature, we can write this as this diagonal term 1, 2, 3. This is your 4, 5 and 6. 4 and 4 they are the symmetric, 5 and 5, 6 and 6 these are the symmetric of diagonal components. So, this is your delta, look at this delta eta I j is represented by this 3 by 3 matrix, P I j k L under compression 1 1 1 2 I and j put together equal to 1, j and k equal to 1 2 3 etcetera. So, you have this 6 by 6 element strain optic tensor, and for SKL, which is also symmetric, we have seen the strain matrix is also symmetric. So, S6, S6, S4, S4, S5, S5 and this is the diagonal element. So, they are very consistent and very conformable. So, we can put an equal to sign and then we can arrange to calculate the individual change in the refractive impermeability or the refractive indices. Therefore, this is a 4 rank 36 element tensor. We have seen that this is 6 by 6 matrix and you can apply this index contract. So, this is very interesting that if I contract these indices, then we can represent this K L L K, putting 1 2 3 for both of them is a symmetric tensor, I j j I that is also 1 2 3 is a symmetric tensor. So, we can compress the indices to represent this. Therefore, now we apply this index contraction to this equation, which will give me this 1 1 x x equal to 1 2 2. So, using this principle, we can now write this impermeability tensor under tens with one index, that is eta alpha and delta eta alpha, which will give me, now I have been able to contract the indices alpha beta S alpha beta. So, change in impermeability, this quantity is now delta eta S, which is we have a convention of repeated index for summation. So, using that, this quantity we want to calculate, this quantity will come from the strain or the propagation of the acoustic wave, and then connected with this for the which is the material property, that is the strain optic tensor, this and this put together will give us the change in the impermeability, that is the change in the refractive indices. And how this change in the refractive indices takes place in presence of the strain, in presence of the acoustic wave or in presence of any deformation, that can be one to one calculated. So, this is under this contracted form, you have all the elements, because earlier the form was like this is 3 by 3, this is 3 by 3, but this is your 6 by 6. So, if I represent it as 1 by 6 and this is 6 by 1, then it is conformable and we can calculate the individual changes. So, this one you see under index contraction, this is also under index contraction and this is also represented under index contraction. So, we have this equation in the contracted form with matrix notation. So, the modified index ellipsoid equation in the explicit form now takes this form, because this is we are well familiar. This is the change in the impermeability, which is attached to this x square, similarly y square and z square, which will come from the diagonal elements of the impermeability, and these are the off diagonal elements, but there is no diagonal off diagonal by now, because we have been able to put them into one column vector. So, these three are the diagonal elements, these are the off diagonal elements, this will appear twice, this will appear twice, and this also will appear twice. Therefore, this 2 has come outside, and this is the general form of the modified index ellipsoid. We will see which of the components will be non-zero, will be non-vanishing, and which of them will be 0, depending on the condition of the acoustic wave and the medium property in the form of the strain optic coefficients. So, this is in the strain optic form, because this delta impermeability 1 can now be represented by this is again in the compressed notation. So, this is how we can write this equation. Now, let us take one concrete example. Any isotropic medium, the photoelastic coefficients, that is the strain optic tensor, is the typical one. That is, in this case we have only P 11 and P 12, these are the two independent components, and rest all other 0. So, we just we just need to know that the two components P 11 and P 12, from there we can construct this tensor, you can see, and this is for the isotropic medium. Well, so for anisotropic medium, this is a typical electro-optic tensor P 11, P 12, P 2, 1 2, 1 1, 4 1. So, some of the elements, some more elements are present, independent elements. So, that we will see for the individual medium when we have the knowledge of these coefficients, then we can actually calculate the changes in the refractive indices. So, this again the dielectric property, we know that delta I j is equal to 1 if this is the tonality condition, and this condition is satisfied by this. So, permittivity, because this is your eta n square I j and this is 1 by n square I j, this and this eta epsilon I j put together, it will be equal, when I equal to j, j equal to k, then only this you will have epsilon 0. So, this is the permittivity relation with impermeability, and just to check that how we get this relation, there is a just one line exercise, eta I k eta I j. So, this is your 3 by 3, this is again 3 by 3. If you take the product of this, only this becomes 1 1 1. So, this is eta I j and epsilon 0. So, this is 1 1 1. So, it is just one line check. Now, if we represent that delta eta I j equal to this, take this one. So, this now you differentiate, then you can represent this delta eta I k, delta epsilon I k and eta I j plus epsilon I k delta eta I j, this is equal to 0. So, if you transpose to the right hand side, will carry a minus sign, then you post multiply with eta I j, both of them. Now, this quantity eta I j epsilon I k eta I j, epsilon I k eta I j, epsilon I k eta I j, if you just change this. So, this in place of this we can write epsilon 0 delta I j. So, that is what we can represent that. If we write in this form, then we can write this in this form, and because this quantity eta k j eta j l can be written as this, therefore, delta eta j, this quantity comes to the denominator, and you can write this in the expanded form with all the indices. We can write that epsilon I m, this is the strain optic coefficient tensor, and this is a strain tensor, and this is a permittivity tensor. So, this is permittivity. So, this is a very useful relation to estimate, to calculate the change in the permittivity from this relation that this change in the permittivity is in the change in the impermeability multiplied by the permittivity, old permittivity tensors. So, and we will use this relation, to calculate the different cases of the acoustic wave propagation, and we can directly use this to calculate the change in the impermeability, and from there we can again calculate the index ellipsoid, and knowing that index ellipsoid we can calculate the change in the refractive indices individually in the principal axis system for all x, y and z direction, and that will help us to construct the equation of n x, n y and n z with the periodicity of the acoustic wave. That is this n, we will see that n x will be equal to some n which is constant plus or minus some delta n into some cosine of the periodicity of the acoustic wave. So, we will be able to represent the change in the refractive indices by using this relation, which will go into the to explicitly express the change in the refractive indices in the 3 mutually perpendicular direction in the principal axis system of the medium. So, we will continue with the different acoustic waves in the longitudinal direction and in the transverse direction for various cases, and we will continue that. Thank you.